So thank you very much for that kind introduction, madam, and thanks to Mindray for giving me this opportunity once again to share my thoughts about cell counters in general. The topic for the day for me is my wish list from a cell counter. And the moment anybody talks about wishes, this is the poem which comes to my mind, which says, "If wishes were horses, beggars would ride." But I really have a lot of things to appreciate for the simple fact that we have analyzers today which are already giving us where lots of things where the wishes have already come true. Now let's see what happened in the last decade or so. If I look at it from my hospital per se, my PowerPoints used to have this backdrop, and of course we have changed and become BLK Max. We've moved on from a typical logo that we had previously to something that we have here now. And this is something which has happened just in about the last 2 or 3 years. And in the meanwhile, we have also seen a lot of change with respect to a lot of digitization all across the globe. And these two gentlemen actually were the people, who looked at having WhatsApp. It got sold to Facebook and stuff like that and made a lot of money. Of course, the gene expression and next generation sequencing has made huge inroads into our lives. We have started understanding a lot of new entities, and there has been revision of many previous classifications. Especially in the last 2 years, when we have seen a significant change in the way we have started living, especially in terms of COVID. My son keeps telling me, "Dad, you would always tell me to be off the gadgets, and now you have given me gadgets on my hand." So the past and the future have really been very different. And if we look at it from the sci-fi today, there is a huge change with the way the things have come up and across all spheres of life, including what we have with respect to the hematology analyzers. So just to give you a brief history, I will talk about the analyzers a little bit. I'll talk about some principles which are already in use, some current analyzer types with their principles and technologies, the usual common unique abilities of the analyzers which are available, and of course the need for making better sense of the data which is coming out from the analyzers today. So let's look at history, and I'm sure a lot of you already know about it or have been through my presentations in the past and have seen these slides. But just to give you an idea that, it was in late 1930s that the cell counters started taking shape, the Coulter, or the principle on which the entire concept of hematology analyzers is based even today, started coming in the 50s. And later on, other parameters started coming up, which included the platelet counts. The parameters kept on adding, and we called it somewhere around 3-part and 5-part and 7-part and 10-part parameters. And in late 2000s today, we already know that we're looking at somewhere around 15 to 25 parameters, which are already existing, and a far more number of parameters, which are also existing, perhaps on the digitization platforms. And if we look at the current era, we're looking at an era of artificial intelligence, and we know a sky is the limit in this case. So now if we look at it, before 64s, it was what we call the macro world. And after 1674, this is what we call a micro world. And that's where the microscopy from Paul Ehrlich and other people came into the picture. And of course, the Wallace Coulter and the Coulter brothers, who gave us the first automated analyzer. So we started with a small time multi-part CBC analyzer, moved on to have a 3-part analyzer, a 5-part analyzer, an automatic hematology analyzer with retic capabilities, looking at nucleated red blood cells, etc. And in 2000s, we had a many part hematology analyzer. And of course, we are still moving on, and the miracles still continue in the era of side of hematology. Now, this is a picture which is showing you the various milestones, which have been like the pivotal milestones in development of counting cells. And of course, the first and the foremost was that of von Leeuwenhoek, who actually identified the cells for the first time, and then eventually development of microscopy, addition of dyes, the first blood count, which went to Carl Verot, and eventually Coulter, who gave us the principle for the first time. So if you look at historically, there has been a huge evolution of hematology analyzers, and we have reached a stage today where we have a lot of information coming in, perhaps not used to the extent that it should be. Now, with the advancement in the hematology analyzer, what improved is not only the counting that we did, the imprecision which we otherwise would have in our manual techniques was significantly lower. Just look at the imprecision which we had in, say, RBC counting or white blood cell counting on a manual platform. It was between 20 to 30%. And if you look at the platelets, it was far higher, almost about 25 to 30% when we do it manually. Now look at it from the automation today. And if you look at the automation, we are observing that the CVs, or the coefficient of variation, has gone down markedly, making it more precise for people to follow it up. Now, these two gentlemen, I know a lot of you would have already seen. These are the young pictures of the Coulter brothers, who actually gave us the principle of impedance based on which majority of the analyzers work today. And of course, the history with respect to this was that there was this, parchment membrane which was used for creation of a hole, a thread, and the needle, which helped us to make an aperture. And eventually, they wanted to get, a patent for this, for which they went across to the patenting authority in the US and tried to ask for a patenting a hole, which they were actually denied. In fact, it was a big issue for them to give a patent for the hole. Nevertheless, the history goes down, and eventually they did manage to get a patent for the principle per se. In fact, if I give you a further introduction into the history, what you will realize is counting of cells was not really done on impedance for the first time. In fact, it was first done with respect to the light beam or the flow cytometry, which is currently being used in majority of the analyzers. So let's look at what the analyzers have. What do we have on analyzers today, and where our wish list would take us later? So if we look at the classical presentations which we have with respect to the hematology analyzers, we know that we have already something called a Coulter principle, which is basically based on the positive and the negative electrodes of the charge between them, and the cells passing through give us a pulse, which is eventually looked at. And depending upon the size of the pulse, we are able to differentiate between various cell types. Like, for instance, in this particular pictorial, you're able to differentiate between various cell types of the WBCs as well. And to add to this, we also had the flow cytometry based analysis of the the cells or the on the hematology analyzer, which was way back done by Epstein and his colleagues and the Tycho and his colleagues on Technicon system, and they were able to give us the differential characteristics of the cells based on flow cytometry. These are their patent graphics which they had given previously, and based on this we were able to differentiate between various cells. Now, if you look at it, you already have the impedance, you also have the presence of flow cytometry, and both these technologies together were able to give you information that was able to differentiate between various cell types in addition to giving us counts. The flow cell technology, I'm sure all of you are already aware, is basically a technology where the light is thrown across onto the cell, and the forward scatter gives you the size, and the side scatter gives you the complexity. Now, if we look at hematology analyzers today, there is a plethora of information which is already available. In fact, if you look at it, these are the RBC parameters across various analyzers which are available today in the world, which includes analyzers from Mindray, from Abbott, from Beckman Coulter, etc. Just look at the number of parameters which are available from them. 32 on the red blood cells, and of course, we're also looking at parameters from the WBCs, which are nearly 27. Then you have parameters which are coming from the platelets. So you have so many parameters which are already available. And to just give them a count, we know that we have almost about 71 to 80 parameters which are available on various analyzers when we're using hematology analyzers today. Now, if we already have such a lot of information, what wishes can I have? Why should I even wish for anything new? The fact is that there are still some issues with automated counters which probably need attention. For instance, if we look at the quantitative data, it is definitely more accurate than what we used to get previously, and this is also ensuring that the peripheral blood film reviews are actually reducing. The important point is that there is relatively poor qualitative interpretation of the data which is coming from the analyzer. In fact, the biggest challenge that we've seen for the last so many years is that the graphical data which is coming out from the analyzers is kind of underutilized. And if I was asked to wish, I would definitely think that all the graphic data coming from different analyzers would be similar, so that we don't have to teach everybody and anybody different graphs coming from different places. So if they could have a standardized, software where all the people would give us similar kind of graphic patterns, then it would make life easier for a lot of people who are trying to interpret it. Of course, a hematopathologist validation has been a function traditionally done by the human being, but this again could be something which could be taken across by the machine, and the machine learning and artificial intelligence could make it better for us. There is also a need for more emphasis on interpretation of automated data and improving the medical decision making, so that if we are able to have the clinical decision making system adherent or involved with the hematology analyzer, it will give us more information which would help us to make things better for us. Now, if we look at further limitations, there are some complex and time-consuming sample preparation, limited number of parameters that can be detected, and a need for blood draw. The lack of capability for continuous monitoring is also something which one, at times can give problems to most of us. So just to give you another example, when we try to look at comparability of reticulocyte counting, let us say that we look at two different, we look at the reference method and compare it with the analyzer A. What we would love to have is something where the comparability would give us a straight line at an angle of 45 degrees to what we are doing. But does this really happen? Not really. In fact, what we have is something which is having a less than 45 degrees angle, or maybe a more than 45 degrees angle. So what is the big fuss all about, automated reticulocyte counting? When we look at automated reticulocyte counting at lower counts, we still have a lot of comparability between various analyzers. But the moment we are trying to go for higher, counts, at higher counts, there is a lot of variability between analyzers. So the comparability of automated reticulocyte counts, and likewise for many other, counts on the hematology analyzers, may be a challenge at some point of time. So this becomes an important aspect. The analyzer A and analyzer B, if we try to compare, they will again give you, counts which are not comparable, and this can potentially create a lot of problem for us to handle. Now, if we look at pediatric samples today, there are still too many issues with pediatric samples, and especially for the simple fact that when we draw the samples are drawn as small volumes in, sometimes even in microcontainers. And the very simple fact that when we take the sample out, we take it out in a small microvacutainer, not with a clean draw of the blood. It gives a small draw, and sometimes we can have these small little microclots, which the instrument sometimes can fail to pick up. Similarly, if we look at the lipemias and the other interfering substances in various analyzers, we still have some things which are wanting. So the issues which still happen to be there existing with the hematology analyzers need to be taken care of. Now, obviously, ye dil mange more. So how I wish a lot of things which could come across, which could help us to give information that would be very precise and would also make sure that we're not giving something which is not true. So what is my wish list? My wish list is pretty comprehensive. I'm looking for a better, more accurate and more comprehensive instrument where there is, collaboration of the data from all the channels together. I would also want to include a few more parameters in the blood, perhaps, have the provision of having the IPF and the PLCR and the MPVs and the other RBC counts, optical RBC counts, etc., all together in one single platform, which would give me a more possibility of working on the same analyzer rather than looking for multiple analyzers. I would also like to see if I could have what is called the detection of rare events of the blood cells, especially when we are dealing with transplants and we have aplasias, we need to look at cell numbers which are very, very low. Again, looking at exosomes or microvesicles and also looking at phenotypes parallelly would give us a lot more dynamism towards the analyzers. Looking at functional changes within the cells, looking at cell-to-cell interactions, detecting tumor cells, in vivo cell deformability, like in sickle cell anemia, and looking for, the poikilocytosis on a hematology analyzer. Again, looking for intrinsic cell membrane disorders where a machine can actually pick it up and tell us that, look, you're perhaps dealing with something like this. Again, looking at counting of platelets when the clumps are already formed in such a circumstance, and give preferably a count to the patient. All this is something which I'm really looking forward to, but hopefully there are, analyzers, and there are possibilities and technologies which are on the anvil, which will give us this information. So let's see what's already there on the anvil and where people are already working on. So if you look at the novel methods which are under development, there are a lot of contrast agents which are now being used, which can give us multiplexing capabilities on the analyzers. This is already being tried and tested. There are new parameters which are being looked at upon the instruments, like for instance, you're looking at subpopulations of cells or counting of microparticles in blood. Likewise, you're also looking at development of smaller footprint analyzers. Generally when you look at analyzers today, which are capable of giving you a lot of information, they generally have a very large footprint. So obviously you don't want to have such large footprint devices. Again, development of in vivo, blood counting techniques. We are all in the era of Fitbit, and we all want to get information from whatever is available on the Fitbit. So there are lots of things like this which are under development as on today. And why would we have new contrast agents, to have all this looked at, is because it is very important to look at the lymphocytes and the immune complexity of the system, especially if you look at COVID today. We all are looking at immunity and immunology and the immunological mechanisms which are taking care of, the disease state in a particular patient. So when we look at newer contrast agents like quantum dots and rare earth metals, they are able to give us far better information. This is something which is already on the anvil and people are working on it. So roughly, lots and lots of things which can happen. Again, when we wish for a portability, we're looking at automated counters which are having a small footprint that I already mentioned, because otherwise, majority of these large and good, beautiful instruments actually stay back only in a larger, setup, in a large, big laboratory, and that's where the work happens. And again, we need to make sure that we are making it available to more accessible areas. Like for instance, in disaster areas, we saw that when we had COVID recently, a lot of people could not even visit the laboratory from the place where they were staying. So again, having and ensuring that we have all this available nearer the patient is extremely important. Again, if we could miniaturize the flow cytometry based analyzers, that would make it very, very good. For example, there is already something which is happening on a chip based spectroscopy for WBC differential, which is also in the process of being looked at. Like for instance, the way we have something called a true PCR, which is for a PCR for COVID, you have similar kind of instruments which are now available for hematology analysis. And again, in all such cases, the quenching, the lysing, and the peripheral blood film evaluation, all of these things will happen just on a biochip, and you're able to give information in the shortest possible turnaround time. What can be more important than the fact that during these testing times and trying times, we needed to look at the peripheral blood films, from perhaps the confines of our homes. In such circumstances, we would like to have what is called automated digital microscopy. And in such case, we would like to have the image captured and then sent across to the people for analysis. And if we look at that, the image analysis would eventually give us information as to what we're dealing with. Something like this already exists. There is digital morphology analyzers, like from various available companies, like for instance Cellovision, etc., where they're able to give us this data on the WBCs, classify them very nicely and beautifully into blasts and various cell subtypes. Even in fact, give us information which probably otherwise to a naked eye sometimes you can just miss. Like for instance, in these cases, you're looking at OR rods, presence of these hairy cell-like cells, and even platelet satellitism. All this can be picked up by the hematology analyzer, digital morphology analyzer, and given across to you in the at a distance, and you can even report it from there. Again, looking at red blood cells is far more tedious at times, and you would like to look at these red cells vis-a-vis the information coming in from the digital morphology analyzers and report it out from there. Validation, again, it would also not only give you this information in the form of the picture, but you could also get quantification of various cell types. So if you look at the various quantities which we're looking at, if you could see the quantities, it's very obvious. You could get the percentage of anisocytosis, percentage of poikilocytosis of all the cells which is there, and which can actually give you information where it can be useful for differentiating various disease states. You're also reaching a stage where we are trying to have a resurgence of image-based blood cell counters. Of course, there was one of these counters which was being made by one of the companies, though they have given it up at this point of time, but it was very interesting. You have the blood which is going into the analyzer, the slide is being made like a monolayered image, and imaging is done. Post-imaging, you're analyzing it on the computer, and based on the computer graphics, you're able to give the information of all the parameters which are possible and available. Again, when you look at it through high throughput lens blood analysis, again, you are able to give exact information what you could otherwise give from the microscopy, and you might not, it probably would even obviate the need of an operator to look at the microscope and give the information. Now, coming to the last but not the least kind of the information which is extremely important, that is about in vivo automated blood counting. If you look at the in vivo automated blood counting, we are all in the era of Fitbit. The Fitbit that we use, we want everything on the Fitbit. It's extremely appealing, potentially non-invasive, and you are able to get this information directly from the transducer ultrasound, which you're using on the watch and the stuff like that. The only challenge is that the cells are not easily identifiable. If we look at the drawbacks at this point of time, the flow is significantly slower, and in vivo optical conditions sometimes can give rise to a lot more difficult situation where we are not able to pick up the information. Again, if you look at the speed of cells, in the body itself, the speed of cells is changing so much that you're not able to keep a very constant, flow of the cells through the transducer to give accurate information. While I may be claiming that this is where the situation is, we still need to improve it further and get it back onto the platform. Now, what's on the anvil today? We have a lot more newer technologies, which people are trying to work on, which includes optical absorption, which includes elastic scattering, which includes ultrasonographic detection, as I already mentioned, some photoacoustic and photothermal methods, and other information where a lot of contrast-based agents are also being used parallelly to give us the information on the cell counting and the smallest and the miniaturized form, where you're taking sample as little as 0.5 microliters to give the information for patient care. Now, I'm sure after making you go through this entire lecture, I would have probably thoroughly confused you as to what do I want and what's my wish list. So if I look at my wish list today, my wish list is pretty simple. My wish list today is I am looking at having a 5 days week, 2 offs, Saturdays and Sundays. Of course, I would like to have a great salary, which I would love to spend. I would like to see the morphology predominantly of the marrows, and I would like to see the cream, the flow, and the special techniques. I would forever want to have lesser number of peripheral blood films to be reviewed by me, and if somebody could take care of my platelet counts and somebody would help me to see the parasites, my life would be a bliss. But is this really what I want? I actually want that my analyzer should not cost me very high. I actually want to have minimal of low capex involvement. I want it to be an idiot-proof instrument, and I would want it to see a morphological state where my reports could get released automatically. So if I'm really looking at that part of it, there are lots of driving and restraining forces which make us work on this. The lab size, the funding, the standalone or the institution-based. Is it 24/7 or is it routine? What parameters? Where do I want it to go? Now, all these issues, and of course the middleware and the AMCs and the CMCs, which keep driving and restraining us from taking the information. But above all, the most important aspect that we need to look at is the money that we have in our pockets to take care of what we are wanting and what are our desires. So while I may have a lot of wishes which might be important for us to take care of, it also becomes very important to realize that it can become potentially difficult for everybody to have the wishes come true. But I sincerely wish that what you're wishing from a hematology analyzer, it really comes true. Thank you very much for your kind attention. I'll be happy to answer questions if there are any.